Hi, I'm Alistair. I'm a games designer, and in this video I'm going to describe how you can build this electronic escape room puzzle, which uses valves and gauges controlled by an Arduino. So here I've got 4 levers, and each one of them controls one of these 4 gauges. Now, for demonstration purposes, I've just got the gauges lined up directly above the levers that control them. But these could be positioned anywhere. And you could make the puzzle more interesting by adding more pipes around the gauges, and that would also obscure which lever controls them. And the way the narrative for this puzzle is presented to the player is that this network of pipes contains some gas or liquid, and players need to use the valves to adjust the pressure in different sections of that network. So perhaps there's a particularly fragile pipe here that needs to be set to a low pressure or have fluid diverted away from it to prevent it from breaking. Or perhaps players want to try to break the pipe network. So they could turn this lever here so that it goes beyond the safe green zone and into this overpressurized section that would actually break the pipes. So you can set any target value you want for any of these levers. The solution I've got set at the moment is that this one needs to be in the midpoint here, and this final gauge needs to be in the green zone. Now when I move this lever to get it there, I want you to pay attention to the relay module that I've got connected here. So I'm going to increase the pressure here. And see, when I move it into the correct solution zone, the relay clicked, this red light has come on, and the relay is activated, which could release a maglock and open a door or compartment, for example. Now this puzzle is now in the correct solution state, and this relay will stay unlocked while that's the case. But if I move any of these levers now to get out of the correct zone, you'll see that the relay goes off. So it's a self-resetting puzzle, essentially. If soon as any of these levers cross out of the correct zone, the relay will relock again. So let me explain a little bit more detail about how this puzzle works. So the levers are just regular plumbing valves that you could buy in any hardware shop. And this is domestic 15mm copper pipe. So you join these together exactly the same way that you'd fix your leaky kitchen tap, for example. The only difference is that inside of the pipes, I've inserted an LED on one side of each valve and a light dependent resistor, or LDR, on the other side. And then I'm using an analog input pin on an Arduino to measure the voltage drop across the LDR. And that decreases as the lever is turned and more light from the LED shines through the open valve. If you want to know more about how that works, check out my previous video in this channel where I describe that in more detail. Now, to explain how the gauges work, let me remove the cover off the front of one of them. And you'll see that I've got, this is 3mm acrylic sort of cover on the front that I've got here. And then underneath that, I've just got a plastic indicator. This dial is a printed insert. And then underneath that, I've got a servo motor. Now that servo motor is being controlled by the same Arduino that is being used to monitor the levers. The protective disc on the front, that's just laser cut from 3mm acrylic. The whole of the rest of the unit here is 3D printed. I designed it in OpenSCAD, and I'll include a link to the STL model which I created in the description of the video below. Now if I just move those parts out the way, and then I will show you the underside of the board to show how these things work together. So it's in 2 parts. These servo motors here, rather than having them wired directly to the PWM output pins of the Arduino, I'm using a PCA 9685 board here. This is a PWM controller that has an I2C interface to the Arduino. So that means I'm only using 2 pins on my Arduino. I'm using a data pin and a clock pin, and I can control up to 16 servo motors from just those 2 pins there. it's got a separate 5-volt power supply there as well, so that the servos are not drawing power directly from the Arduino 5-volt pin. And then on the underside of the board here, I've got my LEDs all wired to common 5-volt and ground connection here. And then I've got my light dependent resistors, which are connected through these resistors here to form a voltage divider circuit. And that's what's being measured at the analog input pins there on the Arduino. Now this is a little bit hard to see, so let me show you a wiring diagram in Fritzing instead. So in the illustration here, I'm showing an Arduino Uno. I was using a Nano in the video just then, but it really doesn't matter. The only requirement is that you're using a microprocessor with enough analog input pins to be able to monitor each of the levers, and an I2C interface that's going to the PCA 9685 board here that's going to control the servo motors. If you wanted to add more than 4 analog inputs here, you could always use a multiplexer anyway to add more analog inputs. So here I have got my levers on one side of them. I've got the LEDs which are inserted into the pipes, and those are being powered by a 5-volt DC power supply that has got a 220 ohm resistor onto the anodes of each LED, and then they're all connected back through to ground. And this is effectively a completely isolated circuit. It's not connected to the Arduino at all, and it doesn't need to be. These LEDs are just going to be constantly lit, and when the valves are closed, they're just not going to do anything. As the valves are opened, however, some of that light is going to shine through the valve and fall onto these light dependent resistors here. Now each of these is wired on one side through to 5-volt on the Arduino, and then on the other side it's connected through a 10 kilo ohm resistor through to ground, and at the midpoint between the LDR and the resistor, that's where we're going to take this yellow input line and read from an analog input pin. So this is called a resistor divider, a potential divider, or a voltage divider circuit. What we've got is we've got 5 volts here and we've got 0 volts at ground here, and that 5 volts needs to be lost in some ratio between the light dependent resistor and the fixed resistor here. And the ratio at which it's lost depends on the ratio of resistances of the two components that are connected in series. So if the light dependent resistor has got enough light falling on it to make it 10 kilo ohms of resistance, well, that matches the fixed resistor here. So the 5 volt here is going to drop 2.5 volts over the LDR, the remaining 2.5 volts over the fixed resistor here, and the reading that we get at the analog pin here will be exactly half of the voltage of, so it'll be 2.5 volts, or when it's converted through the ADC chip on the Arduino, that's going to come out as a reading of 512, because the ADC is a 10-bit chip that gives readings between 0 and 1023. As the valve is opened or closed and that resistance varies on the LDR here, the corresponding readings at these input pins is going to rise or fall. So we can use that as a proxy way of measuring how far the lever has been opened. Then on this side here, we've got our outputs. So these are the servo motors that are going to move the indicators in each of the gauges. Now, it is possible to wire servos directly to an Arduino. You need to use a pin that is capable of delivering a PWM output. So on the board here, that's the ones that are labelled with this little tilde squiggle symbol. So you can use pin 3, 5, 6, 9, 10 or 11. And the way that the Arduino tells the servo the angle to move to is by using something called pulse width modulation. So when you digital write to a pin like this, you digital write a high or a low signal, and that normally corresponds to 5 volts or 0 volts. And that's fine for just turning something on or off. But when you want to set something to a variable value, you don't simply want the servo motor to be on or off, we want to be able to set an angle somewhere between 0 and 180. So pulse width modulation is a way of sort of chopping that 5 volt signal up into a series of pulses, and depending on how long those pulses are, that's going to adjust the signal that tells where the servo is going to move to. So you can do that direct from the Arduino, but if you do that, you're limited to using those 6 pins here which have got PWM enabled, and also generating that train of pulse signals with the correct timing actually uses up some of the hardware interrupts on the Arduino, and that can interfere with other things that your sketch is trying to do, particularly when we're also trying to take a number of analog inputs on this side. What I've chosen to do instead is to offload all that processing of generating the appropriate width pulses for the servos onto this separate board over here. So this uses a chip which is called a PCA 9685. As I mentioned, this has got 16 channels of PWM output. Now this doesn't have to control servo motors. You could use this to dim 16 LEDs instead, for example. But it's a really good way of letting your Arduino concentrate on other tasks that your sketch has to do. And what you do is you connect it just via A4 and A5. Those are the data and the clock pins that go to the hardware I2C interface on the Arduino. And I am including a little library, which I'll show you in the code in a minute, that lets you write the value you want to each of these 16 channels over that I2C connection, and then you just let the board here get on with generating the appropriate PWM signal that will turn the servo to the correct angle you want. That also has its own DC supply here. So the Arduino is running at 5 volts, and I've got the 5 volt line here shown connected to the light dependent resistors and also to the VCC input on the daughter board here. But this power adapter up here, this is actually what's going to be supplying the power to turn the servo motors. Servo motors can draw a reasonable amount of current, and particularly when you're using several of them, if we were to try to power them all directly from the Arduino, we might risk trying to incur too much current draw, and it's better to actually have that from a separate stabilized 5 volt supply instead. So that's what this power adapter up here is for. Then finally at the top we've got our 5 volt relay module. So this is connected to ground and to 5 volt power again, and it's got a signal line which I've got connected to GPIO pin 2, but in fact you can use any spare pin you want about that. You just have to update the value in the code that you're using. And what we're going to do there is when we write a low or a high signal to this digital output pin here, that's going to make or break the circuit between the common and the normally open pins here. That in turn is going to form a connection that goes through this 12 volt power supply to the maglock, or it's going to break it. So this is a very common design pattern that you'll have seen me used in lots of my projects. We've got a 5 volt side of the relay here with a trigger signal, and depending on whether that signal is low or high, we're able to control a higher voltage on this side of the relay, and in this case that higher voltage is a 12 volt DC circuit that is energizing this maglock, and that's going to get released when the sketch that's running on the Arduino has detected that all the levers have been set to the correct position. And here's the code that's running on the Arduino. It's a little bit over 100 lines long, which is pretty small as far as my code projects normally go, and a lot of that is comments, so with a bit of luck it should be relatively easy to step through this. As always, we start at the top with including any external libraries that we're going to make use of, and the main library I'm going to use is this library here, which allows us to interface with the PCA 9685 PWM board. Now, the board itself uses an I2C connection, as I mentioned, so we also need to include the wire library. That's the Arduino's built-in library for any device that uses I2C interface. And we go on to the constants. So these are variables that are not going to change over the duration of the sketch, and we use it to define the pins which our light dependent resistors are connected to. So these are all the analog pins on one side of the Arduino, and also the digital pin on the other side of the Arduino, which is connected to the relay signal. And then we define the target values, so the solution that we want the puzzle to be set to. And this might need a little bit more explaining, so I had to think this through myself several times. So servo motors, generally speaking, rotate 180 degrees. And in some libraries that's defined as values between 0 and 180. And this particular one is defined as between -90 and +90, with 0 being the midpoint in the middle. As the value increases to higher values, that makes the servo rotate clockwise. Negative values are a rotation anti-clockwise. But because we're looking at the gauges from the front, effectively those two directions have been switched round. So if we want the dial to have to be pointing at the right hand side where the green was on my indicator, that is a negative value. And want it to be on the left hand side, that's a positive value. And then finally, we also need to consider that we're not going to set an exact value that the servo has to be set to here. With any kind of analog input, I think it's really important to have a built-in tolerance that you will allow one side or other. And I've got a fairly generous tolerance of 30 degrees here. So I've divided my 180 degrees of movement of the servo motor into those three regions of red, white and green. And I'm setting the center point of each of those regions to be at -60 degrees on the right, 0 pointing straight up and 60 on the left. And then if I allow 30 degrees either side of that, that will take me from 90 to 30 and then 30 to -30 and finally from -30 to 90. So I'm covering all of the degrees of my 180 degrees of movement into three sections centered around 60, 0, -60, and then I'm allowing 30 degrees either side of that midpoint there. So that's a fairly generous tolerance. With these values in particular, you will find that you need to adjust these depending on your exact setup. Not every servo motor behaves the same, and just because they move between -90 and 90 doesn't necessarily mean that 0 is actually their midpoint either. So this is going to be a little bit of something that you will have to adapt on site with what actually works with your particular hardware, but I thought I'd explain how I'd got those values in the first place, so at least you can work out how to change them yourselves. Then we go on to the globals. So globals are variables that are going to be shared throughout different functions of the code. We initiate an object for controlling the PWM daughter board, and we're also going to initiate a second object, which is this servo eval. So this also comes from the same PCA 9685 library, and it's a kind of a helper function that's going to help us convert from the angle that we want to move the servo to the timing of that pulse signal that I described, the PWM signal that it's going to generate. It's just some extra helper functions that we're going to make use of in a moment. We then have two arrays. We've got an array of 4 integer elements which are representing the inputs that we read from our analog input pins here. And we've also got an array of 4 integers that we're going to use for the outputs. These are the angles that we're going to be comparing to our target value angles here on each of the gauges. And we'll just have a little Boolean flag to indicate whether the puzzle has been solved or not. In some of my other projects, I've had a more complicated state machine where the state of the controller is in many different possible settings. So it could be initializing, reset, solved, waiting for input, all those things like that. This particular puzzle, as I mentioned, is self-resetting, so it's basically either solved at the moment or it's not, and you can move between either of those states directly just by wiggling the valves. So it doesn't really need anything more complicated than a simple Boolean flag to indicate that. Then we go into setup. So setup gets executed once when the code first starts up and the Arduino receives power. And the first thing I always do now is to initiate a serial monitor connection at the specified baud rate. So this is 115,000 baud, and then output the name of this file, so valvesandgauges.ini, and the date and time at which it was compiled and uploaded to the board. I do this on all my code sketches now, And even though we are not going to use the serial monitor as part of the actual behaviour of the puzzle itself, this is just a really useful way. When you plug the board in, you've got loads of Arduinos lying around your desktop, as I always do. You can plug it into a serial monitor, load the serial monitor in the Arduino IDE, and you will be printed out what code this particular Arduino is running. The next section here, this is all about initializing the interface that's going to go to the PWM controller. So we begin the I2C interface on the Arduino by calling the begin method of the wire library. And then we also set the clock rate at which that's going to operate. So this is just the default of 400,000 Hertz or 400 kilohertz. We call the reset devices and then the initialize method of the PCA 9685. So all this is just doing is setting it to the default setting state. And we also set the frequency of which those PWM signals are going to be sent. Most servos use a standard phase length of 20 milliseconds. So that corresponds to a frequency of 50 Hertz. So you get 50 20 millisecond waves in a single second. So that's going to be our frequency. Don't worry too much about this. This is all just default settings that you include once in setup, and then you'll never need to edit these again. And finally, we initialize the relay pin that we're going to use to activate when the puzzle is solved or not. And I'm using an active low relay, so I initially set that pin to be high, which I've connected the trigger pin of the relay to. If you've got an active high relay, you'd set that to low instead and set it high later. That's the end difference there. And then we get into the loop function. So the loop function is where the real meat of the code happens, and this just loops over and over again for as long as the Arduino is powered up. And on every iteration of that loop, we perform a series of operations in the same order. So the first thing we always do is to read the inputs from all of our levers. So we've got 4 levers, and we're going to loop over all of them. I've actually hard-coded the value 4 here, but if you wanted to add more levers, you could adjust this to the size of the array of levers that you had. And you'd also need to just increase the number of elements in your array here, so you'd include the extra pins that you'd wired your extra levers to. But assuming that you're using 4, as I am, we're going to loop over all of them. And then this bit's a little bit complicated here. So we could at this point ignore this section here, loop over all 4 of our levers and take a reading from the corresponding pin to which the LDR is attached. But if you do that, particularly if you do that in very quick succession, what you'll find is that the Arduino itself only has a single ADC channel, and what it's doing is it's kind of switching it between each of those analog input pins very quickly in turn. But it hasn't had chance to properly discharge and kind of clean up from the previous reading it took. Sometimes you need to either install a bit of a delay, or an alternative is what I'm doing here, is take a reading and then discard it, basically. So every time we want to take a reading from a new analog input pin, because they're not totally separate from the other ones, they're still going through the same ADC converter, before taking a sort of a clean reading from that pin, I'm going to take 2 readings from it and discard them, waiting for 5 milliseconds each time. And that's kind of, you can imagine that just sort of cleaning out this possible leftover reading from the previous pin. And then we'll take 1 more analog reading, and this time we will store it in the input values array corresponding to the pin that we've read. So we've got 4 pins, we'll loop over all of them, take a couple of readings first of all, but then chuck them away. Like, imagine if you've changed the barrel of beer at a pub and you've kind of got a new keg installed. You always run through a few pints through the pipes first of all before serving the first pint to the customer. It's the same as that. We're going to discard the first few dirty readings, get a nice clean reading, and we'll put that as our element into the input values array. So we do that first of all. The next thing we're going to do is, well, okay, now we're going to set the needles on the gauges to the correct value. So again, we're going to loop over, and I've hard coded 4 because I've got 4 output gauges, but again, you could adjust that. You can have up to 16 if you're using the same PWM controller as I have. You could even chain more than one of those together and have 32 servos if you really wanted to, but I'm not sure that would actually be a very fun puzzle to solve. And what we need to do is we need to set the values of those gauges somewhere to an angle between minus 90, which remember is all the way to the right, or 90, which is all the way to the left, based on the value of the input that we read from the corresponding levers pin. And that's what we're going to do in this line here. So the map function allows you to scale a provided variable from one range of values into another range of values. So let's say you've got a value that was read somewhere on a scale between 0 and 256, and you wanted to convert that into a number between 0 and 10 instead, well, you could write 0, 256, 0, 10. What we're doing here is we're converting from the 10-bit input signal that we read from the analog read here into the minus 90 to 90 degrees value that we want to send to the servo, but we're also flipping the direction over, so we're decreasing the value from the analog input here, but we're increasing the servo output. Remember, that's to do with the fact that we're looking at the servos from the front, so the other way around. And the other thing is, you'll notice I'm not using the full extent of the scale here. Rather than going from 1023 to 0, which is the full range of values that you could actually get returned from the analog read function, I'm only going from 900 to 100. And there's sort of two reasons for that. The first of all is that this is not a perfect input system here. And you'll find that depending on exactly how well installed you've found that LDR and LED inside the copper pipe, you might get a little bit of light leakage at the edge, you might get other things. And remember, this is actually a voltage divider circuit. We're never going to have all of the voltage lost over the light dependent resistor, and we're never going to have none of it lost over it either. So these are never going to reach the theoretical maximums of 0 and 1023 that you can get from the analog reading because of the way we've designed the circuit. So I've basically just taken close to the highest value and close to the lowest value and mapped those to the full deflection of the needle on the servo. But again, these are values which empirically you might want to try playing around with yourself. You can make the servo more precise by increasing these values. That will ensure that there's a greater range of inputs leads to the same range of outputs, or you can decrease them and that will make it more responsive. So it's a trade-off really, depending on how you want that kind of user experience to feel, from moving the handle to deflecting the servo needle. Play around with these values and see what you like. We need to actually constrain the output of that map function as well, because like I said, we're not going all the way to the extremes. It's possible that this map function will give us an output that's less than minus 90 or more than 90, but we don't want that to happen because we'll attempt to break our servo if we did that. So we'll constrain the output into the allowed range of values that the servo can move to. And then what we need to do is we need to convert that into this pulse signal that's going to be sent, which we're going to use our helper function for. So I mentioned that this was a helper object that comes as part of this library, and the way we're going to use that helper is to convert from an angle in the range minus 90 to 90 to a PWM value that's going to be in the range from 0 to 4095. And it is that value there that we're going to set for the appropriate channel on the PWM controller. So this method here, this shows how easy it is to use this library. Instead of doing an analog write to an Arduino pin, which is what you'd do if you were connecting the servos directly to the Arduino, what we're going to do is we're going to call set channel PWM, and instead of giving the GPIO pin number, we're going to pass the channel number. So this is a value between 0 and 15, corresponding to the 16 channels on the PWM. And we're going to pass the pulse length that we want to send to that channel, which in this case we've calculated from the desired angle we want up here. So we've gone from input value 0 to 1023 to angle minus 90 to 90 to PWM 0 to 4095, and then finally that's the value that we're going to set for this channel on the controller. And after that, the Arduino doesn't need to worry about it anymore because this will all be taken care of by that separate board. So that's read the inputs, it's set the gauges. Now we need to actually work out if the puzzle has been solved or not. So again, this is a pattern you'll have seen me used in many of my projects. We're going to loop over each of the values and compare them to the corresponding target values, and we're going to see if the absolute difference between the actual value and the target value exceeds the allowed tolerance. And remember, the tolerance we put at the top of the code here, so we said we would allow 30 degrees either side of these target values, and hopefully that will allow both for imprecision of the player themselves, but also imprecision within the system. As I mentioned, this is not a perfectly linear scale, but in practice this seemed to be good enough for my purposes at least, and I think for most escape room functions. So if any of the values that are read by the gauges lie outside 30 degrees of the target values, then we're going to say that the dial has not been set to the correct position. So the flag all gauges correct we set to false, and if we get through all the way through this loop and that's not been set, however, that means that we know that all of the gauges must lie within the tolerance of their target value. So then we move into checking the solution. So we've calculated whether all the gauges are correct up here. If they are, and the puzzle wasn't previously solved, then the final lever has just been moved to make the last gauge point at the correct position. And if that's the case, we can send a little bit of debug information through to the serial output. We can set the is solved flag as to true, and most importantly, we can set the relay pin to low, and that's going to release our maglock. Alternatively, if the puzzle was solved before, but now the gauges are not all pointing at the correct position, well, that means that the puzzle has just been nudged out of position. One of the levers has been moved and it's no longer correct. So in that case, we'll say that the puzzle has become unsolved, we'll update the flag, and we will re-lock the maglock again by setting the relay pin to high. And finally, we simply have a little bit of debug information here. This is going to output for all 4 of the inputs and all 4 of the outputs the value that is being measured from the light dependent resistor, and also the value that is being set as that angle between minus 90 and 90. And this is really, really useful when you first install this puzzle and you need to set those values for the particular servo motor you're using, for the particular brightness of LED, all those little environmental factors that can make a difference in how this behaves. If you turn this on, what you'll see on the serial monitor is a whole array of the inputs and outputs from each of the 4 channels, and you can use that to make the adjustments you need to make here so that the full deflection of the lever corresponds to the correct full deflection of each of the gauges. But other than that, that's about the only change you should need to make to this code. So that just about brings me to the end of this video. I hope you found it useful or informative, and maybe it's given you some new ideas for a puzzle that you could put in your escape room. As always, I will put the code and the wiring diagrams and the 3D models for the gauges over on my Patreon account. So if you'd like to access the resources for this project or for any of the other escape room tutorials I've put on this channel, do please head over there. I am only able to make these tutorials with the support of my Patreon donors. I want to say all thank you so much. I really do appreciate your support. If you would like to support me to make more tutorial videos in the future, that would be amazing. If you are unable to, or if you don't want to, that's fine. I will continue to put these tutorials on YouTube for free anyway, so you can always still follow along with them here. Other than that, if you have any comments or suggestions, do please write them below and I'll do my best to get back to you. and I look forward to seeing you next time. Okay, cheers, bye.